Hello, everyone. Welcome to Pre-Lecture 7. This will be our introduction to material in Chapter 12. And so if you would like to check your textbook, you can, of course, do that to learn more about kinetics. So again, starting a new chapter, when we're talking about kinetics, what we're talking about is essentially the rate of a reaction, or how fast a reaction will proceed from its reactants to products. And this is hopefully important, or it is important, but hopefully understand it's important, because depending on how quick a reaction goes, we can learn different things about it. We can talk about a reaction mechanism, which we'll get a little bit more into in class on Thursday, but different sorts of ideas about different steps that a reaction may take, including elementary steps, and then any sort of intermediate species that may be present as well. Okay. And of course, being general chemistry, our concept is thinking about what the chemistry is going on. Sorry, within general chemistry, like I've said, we have a concept and we'll put math to that. And so the math we'll be using to describe this are called rate laws. Okay. So within this, we generally think of kinetics in terms of the rate of a reaction. So how quickly does our reactant turn into a product per unit of time? And so this is done by then measuring the time dependence of a reaction. So giving you an example here, we have the decomposition of hydrogen peroxide, which is H2O2, decomposes to 2 moles of water and 1 mole of oxygen gas. And so if we wanted to do a rate expression for this, we could say that the rate of hydrogen peroxide decomposition is equal to the negative change in concentration of the reactant, because our reactant concentration is going to be going down as we form more product. So that change in concentration over some sort of time interval, right? And so if we were to express that in even more mathematical terms using variables, we could say the concentration of H2O2 at some time minus the concentration of H2O2 at a different time is going to, and then divided by T1 over T2 is going to be equal to the change in concentration of hydrogen peroxide over time, right? So your textbook has this example where it actually shows you if we were to measure the concentration of hydrogen peroxide at different times, we can take the difference between them. From that, we can ultimately calculate a rate of decomposition there. Okay, so one thing to notice is that the rate will change over time. So the rate goes down actually depending on how quickly or what the concentration of something is. So our rate will actually change over time. And so we have different ways we can calculate or represent a rate. The 3 main ones that we'll talk about are using an average rate. So if we averaged all these out, we could get an average rate of the reaction. However, that might not be suitable depending on what we're studying. So maybe we look for an instantaneous rate, which would essentially be just this first data point. It's typically an averaging of your first 2 collectible data points represents your instantaneous rates, or rather the instantaneous rates are any 2 data points. So actually any of these 4 could represent an instantaneous rate, whereas if we use the first one, it is then an initial rate. Sorry for that confusion there. So if we were to graph this, we can show that our average rate would be basically averaging these 2 points over time. An instantaneous rate would be either of these 2 points. So difference in time here and a difference in time there. If we find the slope from that, we get an instantaneous rate. And if we do it from our initial concentration to some time, then that is then our initial rate, okay? So if we want to express this in another way, we should factor in our stoichiometric coefficients. And so any stoichiometric coefficient we have represented here by our lowercase numerals. If it is a reactant, we will have the negative sign because, again, as a reaction occurs, our reactant concentration will decrease, our product concentration will increase. So our rate will be equal to -1 over A multiplied by the change in concentration of A over a change in time. that's going to be equal to then a positive 1 over B multiplied by the change in the concentration of B over the change in time. Okay. So bringing this into actual chemical systems, take a moment and see if you could figure out what the rate expression would be for this chemical reaction below. And so I'm going to go ahead and reveal that now. Hopefully you were able to get this, where our rate is going to be equal to -1/2 of our concentration of ammonia, NH3 there, change in concentration of ammonia over change in time, which is equal to, we could say 1 over 1. I did not include that, but because our stoichiometric coefficient is 1 there, we just have the change in concentration of N2, nitrogen gas, over the change in time. Then because our stoichiometric coefficient is 3 there, that will also then be equal to 1/3 of the change in concentration of H2 over the change in time. Okay. If we were to graph that particular reaction, this is what it would look like, to where anytime we have a decrease in our concentration of ammonia, basically 1/2 of that is going to be, or 1/2 of the rate is going to be the formation of N2, or I should say double the rate, and then triple the rate as the formation of H2 gas. Okay. All right, that's our introduction to kinetics. In class, we're going to do a little bit more with colligative properties, just a few more practice problems, and then keep going on the chapter 12 material with kinetics. Hope you have a great day. Please let me know if you have any questions. Otherwise, I will see you in class.